So combinations, permutations, and entries are, or in other words, we're talking about playing cards and gambling.
Oh, okay.
Statistics has come from some very weird places, and one of the main areas it came from was gambling originally.
Okay.
Gambling and probability, which is what we're going to start now. We're talking about playing cards.
Okay.
And this was the sort of questions that people started asking themselves to what eventually led into statistics. To understand what follows, you'll need to understand fractions, you'll need to have some basic algebra.
Okay.
So if you take two...
We're going to make a lot of money out of this.
Yeah, no.
No,
well...
Because it's only probability.
Well, if you study probability, what you'll learn is don't gamble.
Fair enough.
Save
lesson.
Save a lot of money. Yeah, don't gamble unless you are the house, because the house always wins.
Fair enough.
One of the guys who wrote one of the key early books on probability, a guy called de Moivre, his book was called The Doctrine of Chances, and in his introduction he said one of the reasons he was writing it was to teach people there is no such thing as luck.
Okay.
So
multiple lessons coming in, moral lessons and mathematical lessons. Sounds great.
So the first question we're going to look at is, if we have 5 playing cards, how many ways can we sort those? What's the basic option? So to start with, we can pick any one of 5 cards for our first position. So we put the queen there. Now, just going to go back a little bit to multiplication. We did that multiplication video. We looked at 6 fours 24. We said that can be 6 times 24 or 6 lots of 24. There's another meaning that multiplication, or another way to think about it, which is for each of those 6 rows, there are 4 blocks.
Oh yeah, I can literally see that. Yeah.
For each of those 4 columns, there are 6 blocks. So that for each there are is a really helpful way to think about multiplication.
Say that phrase again. For each there
for
are.
each there are, yeah.
Okay.
For each of these there are. Helpful way to think about multiplication when we think about probability. So for each of those 5 cards,
yes,
there are 4 more cards we can pick from.
Oh, that's exciting. I like that. I got that.
Got that? Yeah. So we picked 5 for the first one, and we could pick, for each of those 5 we could pick 4 more. So we picked the 2. That means there are 20 ways we could have got to that part. That makes sense?
And just roll that last bit. I was with you when there were 4, and you just multiplied something, did you?
Yeah. So I multiplied the 5 ways we could have got picked for the first card.
Yeah.
Every time we did one of those, there are 4 more we could have picked from.
Right.
So to get to our second, we could go on the
20.
the 10 and the 4th. So that's going to end up being 20.
Oh yeah. All right.
If you're not sure, you can stop the video and draw that out for yourself.
No,
you got that?
I'm on the bus.
Good.
Might be on the back seat of the bus, but I'm on the bus.
No, because that's the hard bit.
Oh, okay. Happy days.
That's the hard bit. Okay, yeah. For each of those, there are so for each of the first there's 5 ways of picking the first one. For each of those, there's 4 ways. For each of those, there's 3 you could pick. For each of those, there's 2, and for each of those, there's only 1 left.
Yeah.
So that means the total ways we could have done that is 5 by 4 by 3 by 2 by, well, the 1 doesn't really count.
And you multiply those.
And you multiply those together.
Why are you multiplying them? Just remind me again.
Because for each of them, you could have 1.
Yes.
So if we go back a bit. Yep. Go back a bit. We could have gone 10, and that would have then given, so that would have been another one, and then we would have gone plus a queen, or plus a 2, or plus a 4, because that's going to be another 4, and then we could have gone with 2, so we could have done another 4 for those. So there were 5 ones we could have started with, and for each of those we could have had another 4, so that's going to end up being 20 altogether. Yeah, I'm glad you got me to go back, because that's the important bit.
All right.
None of this makes sense unless you get that.
Yeah.
You get that, and that's fine.
So it doesn't actually matter which one you start with in terms of the actual cards.
No,
are irrelevant.
we're just talking about how many we could have done.
Yeah, right. Okay.
So we could have done that 5 by 4 by 3 by 2 by 1 way. Or we could have done that, we could have sorted that 120 ways.
Yeah, right. Okay. Oh.
All right.
I got that.
Got that. Excellent. Now, need some shorthand for that. And there's actually a number of different ways to express this, but the most common one is called factorial. We call it 5 factorial expressed with an exclamation mark, as in outstanding.
Is it in mathematics or statistics that an exclamation mark is a symbol in both?
Yeah, it's a mathematical symbol. Exclamation means 5 factorial. It means 5 by 4 by 3 by 2 by 1.
Does that mean the mathematician got it really excited? Exclamation mark.
I think that probably is the case.
Probably is.
Yeah. 5, and also possibly because these numbers get really big really fast.
Yeah.
So if you want to know, we'll cover this more in the book, How to Love Statistics, but if you want to know how many ways you could sort a whole pack of cards, it's unbelievable. It's like if you shuffled a pack of card every minute from the beginning of the universe 6 billion years ago, you would barely scratch the surface. It's an insanely big number.
Yeah. So just back on that one where you got 120, da equals 120, and which equals 5. So what's the exclamation mark stand for there?
Stands for factorial. It's saying go through this process. Add 5 by 1 less than 5 by 1 less than 8 by 1 less than 1 so 5.
Okay.
So if it was 10 factorial, it would be 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3.
All right.
And that's how many it would be. But so however many cards we've got or any other things we're trying to sort, the number of ways we could sort it is going to be 5 factorial.
Okay.
That makes sense?
Yes, it scarily does.
Excellent. So now, well, how many ways could we just pick, how many ways are there to pick just 2 cards from that? Okay.
So pick 2 cards?
Yeah, just pick 2 cards and in any order, what could they be?
All right.
So there's going to be, 5 ways to pick the first one, and 4 ways to pick the second one, and then we can stop.
Okay. Why did we stop?
Because we only wanted 2.
Oh, sorry. Yes. Obvious. Got it.
So 5 by 4. Now, what we want though, just because it was way too easy, is a way to express that just with the notation we know so far. So just with fractions and that, and it's worth going through this because you see this a lot when you get into mathematical formula, and when you see them, you go, well, where did that come from? So I'll show you where that came from. So if we just wanted to express the idea of 5 by 4, just how many ways can we pick 2 cards out of 5? We'll go, we really don't want that 3, 2, 1 on the end of it.
Yeah.
We need a way of getting rid of that. And we're multiplying 3 by 2 by 1, which is actually 6. And so we want to get, and bear in mind this is an equation, so what we do to one side we can do to the other.
Which is that phrase is the same as, or whatever it was
the same
in the other video. Yeah, right.
3 by 2 by 1 is the same as 3 factorial. So what we've got there is 5 by 4 times 3 factorial. If we want to not show that 3 factorial, we can just divide by 3 factorial. They'll cancel one another. We've got to divide the other side by 3 factorial. So 5 by 4 is going to be the same as 5 factorial over 3 factorial.
Yeah.
So what we've got is 5 by 4 by 3 times 2 times 1 divided by or over 3 times 2 times 1. The 3 times 2 times 1 on the bottom and top will cancel one another out.
Okay.
We'll just have 5 by 4.
Gotcha.
So that's so that 5 factorial over 3 factorial is a way of saying, I'll just do the first 2 and then we won't do any of the others. We'll just take that.
So that whole factorial thing is to simplify what would be going on forever.
Yeah, when people used to write this out, it's actually really hard to follow their writing because they didn't have factorial notation. So it's very hard to read it now and follow where they were at. Factorial makes it. It's a relatively recent invention, but it's much easier to follow. So 5 by 4 is the same as 5 factorial over 3 factorial.
Okay.
To make this a bit more general, where we got the 3 from was we said, well, we're going to just take 2 of them. We're going to discard everything else. So if we didn't want to use that, so 5 by 3, it's the same as taking 5, taking away from that, and whatever's left there when we take the 5 from, which happens to be 3, we're going to discard that.
Yeah, okay.
Does that make sense?
Yes.
So 5 over 5 minus 2 factorial is the number of ways we can pick 2 cards from 5.
Say that one again.
That's the number of ways we can pick 2 cards out of 5 cards.
Okay.
Now, what mathematicians like to do is go, okay, well, that happens in this instance, but how do we come up with a formula that we can apply anywhere? So this is where we're going to use some algebra. And say, okay, we've got that. Now, let's call our 5n for any number you could pick. We could call that a million. We could call it 27. Doesn't matter. Well, call it any whole number of cards. And if we wanted to take 2 of them, and of course, if we didn't just want to take 2, but we wanted to pick any particular number we wanted, well, let's call the 2 r is what they tend to call it. So n factorial over n minus r all factorial is the number of ways you can pick r objects from n of them.
Little epiphany. Right.
So hey,
yes.
How many ways can you pick 7 cards from 52?
Yes.
Now you know.
I'm starting to see a big application to that.
Yeah.
That's very cool.
Yeah, it is actually very cool. It's got
I just had a moment also with algebra to say that click over into algebra, suddenly my vision for it just expanded because, so now we can use this for cards, apples, buildings, people, whatever.
Anything you like, yeah. Study groups, how many ways could we break this up? Anything you want to know. And getting into statistics, a lot of it's about, well, this happened, how many ways could it have happened?
Yes.
So therefore we kind of know, well, so what was kind of going to happen there? Well, it could have happened any of those ways, it happened this way. Does that tell us anything if it happened this way, but it could have happened all those ways? So that's kind of, we're getting ahead of ourselves, but that's kind of the essence. Yeah,
it's nice to just see that, not to get into a detail, but just those little moments when I can sort of go, I can see why that, something that previous for me would have just been like, whatever. Suddenly, when you made that shift from the numbers to the symbols, I went, okay, now you can see how that could be really useful.
So we're close, but not there to saying, well, in, say, the game of poker, there's 5 cards. So any particular poker hand, we're close to being able to say what your chances are of getting a particular poker hand.
Yeah.
Not quite there.
Okay.
Because...
So put my money away, right?
In
fact, put my money away forever.
Put your money away forever.
Okay.
Because what that gives us, it's called the number of permutations. Now, that word permutations, if you think about DNA, which you do all the time,
yeah, I do.
It's just a whole string of little molecules called nucleotides, and there's only a handful of them. I can't remember the exact number, but it's not large, and everything from a little algae cell to you to a kangaroo gets made up of different mutations of those. So different, they get ordered. So just what this is telling you is the order matters. In other words, what we calculated is how many ways to get a particular order. But when we're playing cards, we don't care about the order.
Yeah.
We just want to know they're the cards. We don't care what order they were dealt in.
Yeah.
So somehow we're going to have to reduce. So if you want to know what your chance of getting a particular poker hand is, or any other game of cards, we call it the combination. And it's going to be combinations times something. It's going to give us because there's going to be
number of permutations.
Yeah.
Okay.
But we already know how to calculate the number of permutations. We know how to calculate that rather, which is the number of ways something was ordered. So we've already said when we looked at the playing cards that there's 5 factorial ways of doing it. Or if there's if we're only looking at 2 cards, there's 2 factorial ways of doing it.
Yes. Okay.
So in other words, the number of combinations times 2 factorial, or if we're just being general here, the number of combinations times r factorial, and we just change those around, same thing, is going to give us the permutations.
So then we got the permutations is to use your biological analogy, is the number of mutations.
Number of mutations, the number of ways it can be
possible
can be ordered together of that group.
Of the way they can be ordered together.
Yeah.
Right.
Of that group, which is a combination.
Okay. Yeah.
So what we want to know is, and we've already said that permutations, we did the work earlier, well that's n minus n over n minus r, or n factorial over n minus r factorial, is the combinations times r factorial. So if we certain equation, we can divide both sides by r factorial. That n factorial over r factorial over multiplied by n minus r factorial.
Yeah.
It seems like a lot, but that's the number of combinations. So that formula
Yeah.
will tell you how many combinations of anything you can pick from anything.
Okay.
Really useful formula.
Yeah.
Like what's your chance of getting a royal flush shooting spades in
Okay.
whatever. So yeah, it's basically a fundamental building block of statistics. It's got its own name. They sometimes call it, it gets symbolised like that, n choose r, or sometimes n binomial r, for reasons we'll come to in another video. Sometimes they write it like that, n choose r, or n combination of r, but whatever of those means, that's the formula, and it means how many ways can we pick r objects from a group of n of them.
So just on probably over a couple of our videos, but what's becoming clearer to me is that when you see those big blackboards full of symbols, they're kind of clusters of little calculations going on. So some of it is abbreviations for a whole lot of stuff going on.
A lot of stuff that people are familiar
you get
with.
your head around it.
Yeah.
So there's a convention saying when you see this thing, it actually means this incredibly complex thing that we couldn't possibly write on a blackboard.
Yeah.
So to save us doing that, we're going to put this symbol in, we're going to put that in there, and we'll...
Just a bit of shorthand and we're there.
All right.
Okay.
So that does demystify it a lot for me, John. Thank you.
Excellent. Thank you for watching.